This is our typical copyright. We already mentioned about graph being very important in physics, and that we will split this video into two, because if we try to do one video, it will be too long. So we finish with Physics 22A, speed time graph. We finish with that. We are now doing Physics 22B, distance time graph. So we will be looking at one example. Mrs. Jones left home to go to the supermarket to buy some groceries. She took 31 seconds to travel 250 meters east. She then stopped at a traffic light for 25 seconds, after which she continued east for 45 seconds when she covered a distance of 585 meters, bringing her to the parking lot of the supermarket. On her way back home, she traveled 1.02 kilometers west along a different straight road that took 65 seconds, turned at a roundabout and traveled 185 meters east to reach her home in 21 more seconds. Ignoring time she spent at the supermarket, first, we are to draw a distance time graph to show this trip, this journey. And secondly, we are to use the graph to find the average speed from the supermarket to the time she passed her home going west. So this is a speed time graph, and from the graph, you have to do certain things. Sometimes you are asked to do a distance time graph instead of a speed time graph. So time will still be here, but instead of speed, we'll have distance here. So here is a question. This may be a little more difficult than what you would be required to do for CSEC, but let's do it. Mrs. Jones left home to go to the supermarket to buy some groceries. She took 31 seconds to travel 250 meters east. She then stopped at a traffic light for 25 seconds, after which she continued east for 45 seconds when she covered a distance of 585 meters, bringing her to the parking lot of the supermarket. On her way back home, she traveled 1.02 kilometers west along a different straight road that took 65 seconds, turned at a roundabout, and traveled east 185 meters to reach her home in 21 seconds more. Ignore time that she spent at the supermarket. 1. Draw a distance time graph to show the trip. And 2. Using the graph, find the average speed from the supermarket to the time she passed her home going west. In this case, we may need to make a little drawing so that we can clearly understand what is happening. Let us say this is Mrs. Jones' home. She left here. She traveled 250 meters in 31 seconds going east. This direction is east. She stopped at a traffic light here for 25 seconds. Then she traveled another 585 meters for 45 seconds going east, still going east, and she reached the supermarket. On her way back, she took a different straight road and she traveled 1.20 kilometers in 65 seconds going this way, and in the process, she actually passed her home and went to the roundabout, turned around like this, and traveled the 185 meters in 21 seconds to reach back home. She was going one direction east, she turned around and came back this way. She passed her home and went this way and actually traveled back east again. This is a little more complicated for the simple reason that now we may have to use more than one quadrant. So let us just make a little sketch. All right, this is time. This is distance. So she traveled that way, that way, that way. She reached the supermarket. That's going away from home, east. Coming west, she traveled this way, But then she passed her home. And then she had to travel back a little way to get home. So this is the outward journey from here to there, from here to there. This is the home journey, but she traveled this way, passed her home, and then turned around about here and came back east, and she reached home. Now notice, in this case, as I said, we have to use two quadrants. This first one here and this fourth one here. So it's a little more complicated than this speed time graph that we just did. Here's our graph paper. Our x-axis will no longer fall here. Our x-axis will fall somewhere in between here. So let's see how that works out. We're going 250 meters east, followed by 585 meters still east. That's 250. And that is 835 meters east. Now when we go west, 835 meters east, so go west like that, 1.02 kilometers, which is 1,020 kilometers, 1,020. So now that means if we take out that 835 from the 1020, we have 85 meters in the opposite direction. So we'd have to begin not in the middle here, because this, you see, this way is 835 and this one is 185. Up here would be 835 and down here would be 185, wherever we put our x-axis. So you have to work this out, and let us say, if you begin here, if you begin there, do a little trial and error here. We could go 10, 20, no, that's not going to work. 100, 200, 300, 400, 500, 600, 700, 800. Let's go in 50s. 50, 100, 200, 300, 400, 500, 600, 700, 800. Let's come down here. 100, 200, 300, 400, 5, 6, 7, 8. And this way, we want 185, so we need about 200, 100, 200. So, okay, we can start here rather than there. So what we'll do, we will draw our x-axis here. And this will be our y-axis. So this is our x-axis. And we want to fit 187 seconds along this x-axis. So this is time, and it is measured in seconds. We want to fit 187. Never mind these individual numbers. We just add them up to find that we need at least 187. So we'll try for 200. So let's see. If we start here and we go 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, we can't get 200. So let's go 20, 40, 60, 80, 100, 120, 140, 160, 180, 200. So we have used half. Okay, so we can use that. So remember, this is 0. This is 20, 40, 60, 80, 100, 120 exactly under that mark, 140, 160, 180, 200. We can stop there. Our scale here is 1 centimeter equal 20 seconds. The sensitivity is, now if from here to here is 20 seconds and you have 5 divisions, then 20 divided by 5 will give you 4 seconds. Now keep that in mind. So 4 and 4, 8 and 4, 12 and 4, 16 and 4, 20, 24, 28, 32, 36, 40, and so on. Now on this axis, well, we already kind of scale it out. We are going to put, well, we can write it out with 100 here, 200, 300, 400, 500, 600, 700, 800. That's 1, 2, 3, 4, 5, 6, 7, 8, 900. And this way, this would be negative 100, negative 200. We could have dropped that a little, maybe to this line here. So we're writing here, this is distance in meters, and the scale here is 1 centimeter equal. Now remember, 1 centimeter is from here to there. So we have 2 centimeters here being 100. So 1 centimeter would be 50 meters. 50 meters. And the sensitivity from here to here is 50, and you have 5 little divisions here. So one of those smallest divisions would be 50 divided by 5, which would be 10 meters. So now that we have that, we can plot our points. That is about the hardest thing to do on graphs. To scale out your axis properly and make sure you have the right variable in the right axis. So she took 31 seconds to travel 250 meters. So 250 meters will take us here, and she took 31 seconds. Now be very careful. We said that each of this little division here is 4. So it's 20, 24, 28, 32. So 31 would be almost 32. Almost 32. So you could follow that line and go up there. Almost 32. The little mark here. By the way, just to make sure you don't lose your way, you can always draw a very, very light line or draw a broken line here. You are estimating that. You can't measure it exactly. You can't find it exactly. So this is the first part of our journey. She stopped at a traffic light for 25 seconds. So now we will add 31 and 25, and we will get 56. So let's see where 56 is here now. That's 40, 44, 40, okay, 56, 60. 56 is exactly here. We could find that on this line. So we go up 56, come across here at the 250. Now this is the time while she is waiting at the traffic light. She then traveled 585 meters more. So that's 250 plus 585 will give you 835. So let's go see where 835 is. That's 800. Remember, the sensitivity here now is 10. 8, 810, 820, 830, 840, 835 would be exactly halfway between there. And we could draw a very, very light line coming across like that. That's our 835 line. And the time she took to do that was 45 seconds. So 56 plus 45, that would give us 101. So we go to 101. By now you know that each of this little division here is 4. That is the sensitivity on this axis. And by the way, each axis, equal distance must represent equal amounts. So if 1 centimeter represents 20, the next one will represent 20 more, which will bring us to 40, and then another 20 more, which will bring us to 60, and so on. On this axis, 1 centimeter is 50. The next centimeter would be 50 more, which will take us to 100, and 150, 200, and so on. You cannot do something like 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 120, 140, 160. You cannot do that. The axis must be evenly spaced. Okay, now that we have that, 101, this is 104, that's 102. 101 is almost close to that 100. So it's very, very close to that 100. So we could put it there. Very close to the 100. So we can draw this part of the journey. Now remember, this is a distance time graph, not a speed time graph. A distance time graph. So we draw in this piece here. Okay. Now that's the outward journey. She has reached the supermarket. We are not going to deal with how much time she spent at the supermarket. She did her shopping, and now she's going back home. Remember, we said she traveled a different route, and she traveled 1.02 kilometers for 65 seconds, going in the opposite direction. So she passed her home. So that will take us 1020 minus the 835 that she went out that way, so 185. So she passed her home by 185 meters. So that's 100, 10, 20, 30, 40, 50, 60, 70, 80, and halfway between there, 185. So in case we lose our way, let us draw a light line here to keep us on track. That's how far she went. And how much time did she take? She took 65 seconds. That's 65 seconds more than this 101. So if you add 65 to 101, you get 166. So now we have to go to 166, 160, 164. Remember, the sensitivity here is 4 seconds. 164, 166 would be halfway between here. So if we take halfway between there and come down halfway, we are going to arrive at this point, put a little circle here, and now we draw her journey past her home. From there, all the way there, and now she has to go back this distance in 21 seconds. So if we add 21 seconds to 166, we get 187. So we get 80, 84, 88, almost there. Almost there. As I said, this is a little more complicated than what you are expected to do for C-sec. You will not have to go in the negative distance. You will just deal with up here. She goes out like that, stop and come back like this, come back like that, and stop here. But I'm just doing this as an example so you could see. So you could see what may be required of you. All right, now that you did that, you did the distance time graph. And then we want to find the average speed from the supermarket to the time she passed her home going west. In other words, we want to find the average speed from here to here. Now the gradient on a distance time graph is the speed. Now, we know from here to here is 835. So this here is 835 meters. We know this point here was 101. That point there is 101. Now we have to estimate this point here because we don't have a measurement for that. 40, 44, 48, 52, 54. Looks like that is 54. So, a gradient on a distance time graph is the speed. So we get the gradient is equal to increase in y is equal to, I'm just going to use delta y over delta x. And in this case, it will be 835 meters over, so we know this is 101. We estimate this as 154. We subtract 101 from 154 and we get 53 seconds. If we divide 835 by 53, we get so the speed is equal to 15.75 meters per second. We have too many significant figures there. We have to round that off to two significant figures. So because we estimate this as 53, that's approximately 16 plus or minus 0.5 meters per second. And that brings us to the end of video physics 22B, distance time graph. In the next video, physics 23, we will consider a graph involving spring constant. We will also be dealing with extrapolation and line of best fit.